Alia University in Kolkata, India, and subsequently he spent 2 years as a researcher at the Indian Institute of Science, Education and Research, ISER, in Kolkata also. He has authored approximately 26 articles in Index Journal and has received more than 140 citations to his work. His research focuses on the application of information theoretical tools to atomic systems and other physical models, with particular emphasis on understanding how confinement affects their properties. The talk of today, I mean, the title of the talk is in his slide. So let me give the microphone to Shantanu. And please go ahead, Santanu. It's a pleasure being here.
Thank you, Professor Humberto, for the nice introduction. Again, a very good morning and evening and afternoon to all of you. Before start, first I should say I should thank the organizer for giving me the opportunity to present my work here. As you can see, the title, as you can see from the title of my talk, today I shall talk about the feasibility of Shannon and Fisher information entropy in a dynamical system, particularly in the context of scattering theory. For this, I shall start from the very fundamentals of the scattering theory. This is the classical scattering theory or the Rutherford scattering. From there, I shall try to connect the classical scattering to the quantum scattering to introduce the quantum information theory. And as an applications, then I shall consider the first example of the scattering of a single particle in a square wave potential. And subsequently, I shall discuss about a real scattering of photon and hydrogen. So let us start. In 1911, Rutherford did an experiment where he considered a very thin slice of or very thin slice of gold foil, and he bombarded it with alpha particle. And he observed something very remarkable. And in his own word, like it was quite the most incredible event that has ever happened to me in my life. It was almost as incredible as if you fired a 15-inch shell at a piece of tissue paper and it came back and hit you. And the main key observation of that experiment is that for case of atomic structure, the atom is almost empty, and there exists a dense and charged nucleus at the very center of the atom. Now, if we do a little bit of mathematics, one can calculate the differential scattering cross section, which is nothing but the angular distribution of scattered particle, which depends upon the diffraction angle, which I have shown here as a theta. And the interesting thing is that this differential cross section has a strong dependence on theta. And the most important part, the larger or large angle scattering is very rare, but they are very informative. And this angle, that theta, that establishes a direct mapping between the angle and the impact parameter. And the relation between the angle and the impact parameter I have shown here. So the relation I have shown here, this we can say is the first information extraction law. Why? Because the angle that can be measured from laboratory, and from this angle we can extract some inner structure of an atom. So we are getting some informations by or through some measure or experimentally available measurement. That's why one can say this is the first information extraction law. But while we are treating the classical scattering or Rutherford scattering, in which it follows some deterministic trajectories under Coulomb forces. Therefore, there are some limitations in the classical pictures, like we do not have any interference or diffraction or any kind of tunneling behavior we can observe. Therefore, we we lack a measure of probability distribution, or we cannot apply the information content as we understand. For this, what we need to do, we need to replace the trajectory with a wave functions. And therefore, the whole problems become a wave packet evolutions, which is governed by the time-dependent Schrodinger equations. And by solving the Schrodinger equation, one can find out the wave functions and therefore the density. And one can apply this density to calculate various information measures, just like Shannon or Fisher information entropy. Now, when I'm talking about the classical and quantum information entropy, I shall quote James Gleick from his books, The Information in History, A Theory of Flat. The book came in the year 2011. In his book, he quote like, for Wiener, entropy was a measure of disorder. For Shannon, of uncertainty. Fundamentally, as they were realizing, these are the same. And we all behave like a Maxwell demon. We propagate structure. We disturb the tendency towards the equilibrium. It sometimes seems as if curbing entropy is our quixotic purpose in the universe. This is the same, or this is very true for me or my group, that we are also trying to find out something with respect to the entropy. Now, over the few years, we have tried to understand how that information theoretic measures or the tools can be used to understand the atomic structures for case of stationary state. Therefore, right now, what we are trying to answer, the following questions. Does the quantum information entropy speak a universal language to describe the complexity, predictability, and information flow in a dynamical systems? That's the questions that we are trying to find out the answer. To answer this, let us first consider the case of a particle scattered from a square wave potential. And it is a very textbook problem. The Schrodinger equation, here you can see the Schrodinger equation, which we can solve, and it is available in any books. Here, what we consider, we consider a scaling following this, and the energy is redefined like that. And therefore, the Schrodinger equations, can be written like this, where this beta that depends upon the mass of the particle as well as the potential parameters. V0 is the depth and R0 is the width of the square wave potential. And if we solve that, considering three different regions, region 1, which is the reflection region, the capture region, and the transmission region, one can find out the coefficient of transmission as well as the reflection. Here I have shown the coefficient of the transmission. It is available in the books, any standard quantum mechanics books. And in terms of beta and epsilon, I have shown that the transmission coefficient. And so one can find out the energy of the systems. Now the interesting part is that the argument of this sign, if they equals to n pi, there we find there is a resonances, and at that resonance conditions, the transmission coefficient will be maximum. That likes when the particle comes, it will not feel any potential, just the potential will feel like to him like a transparent medium. It will just pass. Okay, and this kind of resonances is called as a Ramsauer-Tausen effect. But if we try to implement the information theory directly in this problem, there is an issue. Because if you look, or if you just recall, that for both reflection and the transmission wave, they are plane wave. And the plane wave cannot be normalized. Therefore, the information theory is not works there. For information theory, if we need to apply the Shannon or Fisher entropy, the wave function of the density, this has to be normalized. Now, instead of considering the plane wave or these solutions, what we can consider? We can consider the particle as a as a Gaussian wave packet with sufficiently high width so that it exactly behaves a free particle. Here I have shown two different scenarios of two different energy of the particles, and you can see when the particle passes through the squirrel potential, it's divided into two parts. One is the transmission and one is the reflection part. And depending on the energy, sometimes the transmission's probability becomes higher or dominates, or sometimes there is also a transient part of the reflections. Now, to solve the problem, the Gaussian wave packet we consider, which has this form, as you can see, which has a width omega t, and that width also varies with respect to the time. To solve the Schrödinger equations with this Gaussian wave packet, we have considered Crank-Nicolson method-based or finite differences method-based Crank-Nicolson approach. For this, we need to evolve the wave functions, the psi. And the wave functions can be evolved with this operator involving the Hamiltonian. From here, to employ the Crank-Nicolson, what we consider, first we consider a function fx, which is only the exponential part involving the potential. And we define the psi in this way, so that when we consider the finite differences to define the double derivative involved in the Schrödinger equations, the Schrödinger equation will just become a eigenvalue problem. And the matrix, what we can have, this m plus or m minus, they will be an triangular matrix, tridiagonal matrix with the following elements. The following elements will look like this. And this nu, that will depend upon two parameters. One is with the mesh size of the dimension of the x, and one is the time mesh size. To get a very converged results, this nu has to be very, very less than 1. Now, in our work, we consider all the essential parameters like this delta t, delta x, or total length of the space, or the initial width of the wave packet very judiciously to get the best possible results that we can have. Therefore, by solving the matrix equation, one can find out the eigenvector and or the wave function of the systems, and from which one can find out the density or the probability density of the system. And that probability density is dependent on both position and the time. Here, what I have shown the probability density distribution as a function of position and as a function of time. For beta parameter as 5. As you look, for a low energy, when the particle is moving and around x equals to 0, where the potential is situated, there happens a disturbance in the density. The reason for this, when the wave packet was moving, at the potential, there generates a standing wave. And from that, the wave coming from the two wall of the potential, they interfere. And this is the actually characteristics of the interference happening within the wave. After that, the post collision, a part of the wave packet reflected back and a part is transmitted. For this energy, you can see the dominant part of the probability is the transmission, as you can observe. But when we increases the energy, then we can see the reflection parts also become significant, although the transmission is dominant here. Now, if we changes the beta value, even for very low energy, we see the interference is happening here, and most of the wave packet is reflected back. And if the wave packet energy is very high, you can see from here, then just wave packet passes through the potential. It does not have any kind of interference. So the dominant part is the transmissions. So you can see there is a dependence of the reflection and transmissions on the energy as well as the beta impact parameter. For further details, I have shown here for beta parameter 100, and you can see the intricacy of the probability distributions in the time evolution step. Now, what we did, since we have calculated the density, from the density, we calculate the reflection coefficient, transmission coefficient, as well as the trapped coefficient. Following this, just we have to integrate within the specific region to have all these coefficients value. In the first panel, in the first column, what I show is the variation of this reflection, transmission, and the trapped coefficient as a function of time. And for three different energy, if you look at the top panel, this blue color line, this corresponds to the reflection, and red color one is the transmission, and the black color one is the trapped. Now the thing is, when the particle with energy, suppose with energy 10, when the particle was coming and it was far away from the potential well, there was no transmission was happening. So the most dominant part was the reflections. But as it interacts with the potential, the resonance happens, and most of the part is contributes to the transmissions, and a fraction of which comes to the reflected. And as we increase the energy, you can see for energy 0.1, not only the dominated part is the transmissions, but there is also a significant dominated part of reflection is there. And this behavior we have tested for different kind of beta parameter. Now, at the end of the collision, if we calculate all these parameters, obviously the trap coefficient which only exists during the collisions, they will not appear. We can find out the reflection and transmission coefficient as a function of energy. For that, we have considered the energy from 0.01 to 10 atomic unit. And you can see something very interesting here. For example, if you concentrate on the second panel, you can concentrate on the first panel also, but let us concentrate on the second panel. Initially, the most dominated part is the reflection for low energy. Now, as the energy increases, there is a point when the reflection becomes 0, but the transition probability, transmission probability become 1. So this is because of the Ramsauer-Townsend resonances that I was talking about. And you can see these oscillations, or there are several points when these resonances occurs, even at high energies, as you can see, or even at low energy, the whole wave packet transmitted through the potential like it is a transparent medium without having a significant amount of reflections for different beta parameter I have shown. Now, since in my hand I have reflection and transmission coefficient, and I have also the total density in my hand, so I did two things in the following slides. First, I consider an approximation that after collisions, the wave packet for the reflection and the transmission I am having, we consider both the wave function as kind of a Gaussian characteristics. So from that approximation that both transmission and reflections, the wave packet will be Gaussian, we try to provide some analytical expression of the entropies. And from the direct measure of the density, we have also calculated the entropies, and we try to compare them so that we can also have an analytical expression of the entropy. For that, what we consider? We consider the normalized reflected wave packet like this, where this higher is a kind of a Gaussian reflected wave packet. And here I have considered the similar way, the normalized transmitted wave packet. And therefore, we have calculated the probability density. And this overlapping term will go to 0 because after post collisions, there will be no overlap between the reflection and the transmissions. And this is another approximation we have considered. Following this, we have calculated the Shannon entropy, which has these forms. We have been able to provide an analytics forms. And also we have calculated the total Fisher entropy. Unlike in the Shannon entropy, in the total Fisher entropy, we find that they don't depend upon the transmission and reflection coefficients. Now, here I have shown the variation of the entropy, Shannon entropy, coming from the reflection, transmission, or trough as a function of time. In the above, you can see initially the wave packet, when was coming from far away from the potential, it has a particular distributions. For that, the reflected Shannon entropy is almost constant. Now, after the interactions, the maximum part of the wave packet transmitted through the well. Therefore, the Shannon entropy for the transmission, it increases, but it decreases for case of a reflection path. And a very transient part of the trapped Shannon entropy we have been also observed. Now, at the end of the collision, if we plot with respect to the energy, and here what we have done, the symbols, they are representing the actual numerical value estimated from directly measured density, and the line within them, they are representing the results which are calculated analytically directly from the Gaussian wave packet. And we find that those measures are really match each other. Another important thing from that, just like the transmission and reflection coefficient, we saw that the entropy can also sense the interference, and it also show the Ramsauer-Townsend effect. So we can say that Shannon entropy can also be used as an indicator of the interference or the Ramsauer-Townsend effect in wave packet interacting with the potential well. Just like this, we have also calculated the Fisher entropy, and we have got exactly similar kind of characteristics. The only thing we have observed in atomic structure, when we consider the atoms under some kind of confining environment, we always see that the Shannon and Fisher entropy always behaves like conjugate to each other. But here, what we have observed with respect to that energy, the Shannon and Fisher entropy almost behave similarly. And this is because of the dynamics happens here, and we understand that this conjugate nature between the Shannon and Fisher entropy is not universal. It may depend upon how ordered the system is, because the Fisher entropy only measures the order. It may be delocalized or localized, but the Fisher entropy give you the information about how it is ordered. So here what we have a similar kind of characteristics for Shannon and Fisher entropy. The work I have shown here is already published in Physica Scripta. I would suggest all of you to go through that article. They are not only the information entropy, we have also considered different kind of other aspects, other properties. And now, if we come to the second problem, which is the dynamics of a real scattering, for which we have considered proton and hydrogen collisions. For this, we have considered the hydrogen, which is in the ground state, is considered as a target, and there is a projectile coming, which is a proton, H+. Now, if the scattering is elastic, then we know the scattering channel is like this. the target will or projectile will have some transfer of momentum or something happen. Now the interesting thing, if the scattering become inelastic, depending on the impact parameter and the collision energy, we can have different kind of channels. Like one can have the charge exchange, like projectile can capture the electron of the target, or the target itself can be excited, or there can be ionizations that can happen. Okay, from the animations in the left side, you can give an idea depending on the impact parameters what could happen. Now, in order to solve this problem, again we have to solve a time-dependent Schrodinger equation. Now the time-dependent Schrodinger equations look like this. Since we have hydrogen atom with a heavy projectile H+, here we consider a semi-classical approach, within which the projectile, that is H+, or the proton, is treated classically, and it follows the Newtonian equations, and the hydrogen or the electronic motion is considered quantum mechanically. For that, we calculated the force coming from the nucleus, and also the force because of the Coulomb repulsions, proton-proton Coulomb repulsions, and also the electronic force. And to consider the actual trajectory of the projectile, we choose velocity Verlet scale, for which what we have done, first we calculate the force, then at a particular time step, we updated the position of the particle as well as the position of the velocity. Then again, we calculate the force, and with that force for the next step, we updated the position and the velocity. So that is how we got the actual trajectory of the projectile. And now what we have done, we have to consider again the Planck-Nicholson method, where we have to take the time evolution of the electronic wave functions. Here, to represent the problem in 3 dimensions, we have considered the Cartesian grid. To give an idea of the Cartesian grid, what we have considered, at the origin, we had the hydrogen atom, and we considered the projectile is moving along the z-axis. And the dimension we consider for the z-axis from minus 30 atomic unit to plus 30 atomic unit, sorry, to 90 atomic unit. And along the x-axis, we consider the impact parameter. Here you can see there is 2 different color of big box, like the black one and the blue one. The region between this blue one, we consider a masking function so that we can have a smooth probability density at the boundary. And here you can also see 2 different boxes separated by this plane. The left plane is considered as the target region, and this box is the excitation region, sorry, the capture region. And in the in below what I have shown, if we consider that the electron, it will have an effective electron cloud, and the projectile is moving through that electron cloud with a real trajectory, and they will interact to each other. First, what I have shown, after the time evolutions or the dynamics, I have calculated the total wave function of the systems. And therefore, we have taken a projection of the density by integrating out our x and y coordinate. And we have the density with respect to the z. And you can see that this 0, this region 1, which is the excitation region, and this is the region of the capture. Now, when we have a very high energy, then what will happen? The proton projectile will come and there will be very less time to interact with the hydrogen target, and it will just go through. So it can only then excited the hydrogen target. That's why you will see for high energy, the excitation probability is much higher and the capture probability is very less. When the energy decreases, you can see the capture probability increases because of the interaction or the longer interactions between the hydrogen atom and the projectile. For that problem, we have considered a wide range of projectile energies from 1000 kilo electron volt to 0.1 kilo electron volt. And for high energy, you can see the dominant part is the excitations. But when the projectile energy decreases, you can see that sometimes the capture probability is higher, or sometimes the excitation probability is higher. Okay, but we have seen that in region 1 and 2, there is no overlap between the probability density. So what we did, we write down the total wave function of the system as a sum of the wave function of the target and the sum of the wave function of the projectile. And the state of the target of the projectile, we can expand it using LCAO like that. And by projecting this state on the total wave function, we have estimated the probability of the excitation in different state like 2s 2p or higher excited state, and similarly the same thing for the capture in 1s 2s 2p. So by different state wise, we have calculated the probability of capture or the excitations. Now from this discrete value of the probability, one can define the discrete Shannon entropy. And this discrete Shannon entropy will give you the contribution of the Shannon entropy in the total entropy coming from the particular state we are considering. For example, if we consider the one state, so it will show you the contribution of the one state in the total Shannon entropy in the excitation or in the capture. For that, in the left hand side, I have shown the variation of the Shannon entropy in different excitation. As you can see, the excitation Shannon entropy for 2p states has a dominant channel. Like for high impact parameter, the dominant channel will be the 2p states. But for a very low impact parameter, one can see that the dominant channel is still the 2s excitations. The similar thing we have seen from the captures, but a very interesting thing we have find in the capture for a very low energy and very low impact parameter, we have seen some kind of oscillations. And this is because when the projectile is coming and it coming with very less energy, it has lot of time to interact with the target. And during the interactions, there creates a transient H2 plus molecular ion. And the states available, or the transient states like 1s sigma or 2p sigma, all those transient states, they interfere to each other. And if you calculate the phase of that interference, that phase depends on that phase shows oscillatory characteristics. And because of that, we are getting these oscillations, and this oscillation is referred as a Stackelberg oscillation. Now, what we observe from here, that how the Shannon entropy contributions coming from the different states, we can estimate. Now, what happens when we have a hydrogen atom? It has a particular electron probability density distributions. Now, because of the of the collisions, this density distribution will be disintegrated, part of which uh, will be captured by the projectile. So there will be a capture density or that excitation density, and depending upon the nature, this density distribution can be localized or delocalized. For that, what we did, we also calculated the excitation and charge transfer or the capture Shannon entropy. And this entropy will give you the notion of how the probability distribution for the excitation or capture, whether they are very localized or they are very delocalized. Here, what we see that for high energy, the hydrogen atom, the only possibility it could excite, or it could be still in the same ground state. So for high energy, what we find that the excitation probability or the entropy is exactly like the hydrogen 1s state, which is the value is around 4.14. But in the low impact region, we find that when the H plus particle was coming, the probability distribution is more dispersed or more delocalized, and it becomes localized to have hydrogen-like characters for high impact parameters. Now, if we decrease the energy, we find something very interesting. Like for some impact parameter, the excitation probability or the capture probability, they are very localized or very delocalized. For that, again, the reason is the same, the Stackelberg oscillations. We are getting this kind of oscillation in the Shannon entropy also. Further, we have calculated the Fisher information entropy. Here we have find that the Shannon, the characteristics of Shannon and Fisher entropy almost conjugate to each other, and as it gives you the notion of the localizations, one can find the exact how much localization or delocalization will happen. One can see from that also. One more thing, the Fisher entropy, one can also see that it can also sense the Stackelberg oscillations. And further, we have calculated, and first we have shown that total differential Fisher entropy can be written as a sum of the entropy coming from the kinetic energy, and another part is coming from the current density. Therefore, we have plot the difference of this 8mk and the fd, which is basically these terms, or the current part, or the flow of the probability we have plotted here. As you can see that during the collisions, sometimes there are capture is happening. So because of the capture, the electron flow is increases, and we are getting a sharp change. And in sometimes for low energy, again during the transient state or during the transient molecular state, the capture happen, but at the end of the collisions, maybe the hydrogen atom still contain the electron in the target. That's why we are getting this kind of characteristics. And also you will see some oscillations, and this oscillation is not related to some characteristics of the target and projectile. This is coming because of the egg box effect, the mesh size we have considered in our calculations. And here I have shown the same difference with respect to the impact parameter. And for less impact parameter, we can see the current also shows this kind of Stackelberg effect. And this is inevitable because in the current, the phase or the Stackelberg phase is there. So as the phase is oscillating, so that current also will oscillate. The work I have shown for proton-hydrogen, it is yet to be published, and we are still doing a lot of different other aspects of the information and other aspects of the collisions. Therefore, I would really like to have some suggestions from all of you, if you have, or we are also open for any kind of collaborations. However, now what we can conclude from these two works? First of all, in case of differential Shannon entropy, we have seen that Shannon or Fisher entropy, they can effectively change the spread out of the wave packets, whether it is localized or delocalized. And also we have seen from the collision of the wave packet with the square wave that it can sense the Ramsauer-Townsend effect. So we can simply say that Shannon or Fisher entropy can be used as an indicator of the Ramsauer-Townsend effect. And similarly, for case of proton-hydrogen collisions, we have seen that in here also Shannon or Fisher entropy can be considered as an effective measure of the collision and also as an indicator of the Stackelberg oscillations. So I'd like to thank my group at ICF, particularly my super energetic boss, Professor Trujillo. And I also want to thank Digapa for sponsoring me, my postdoc here in Mexico. I also want to thank my group in Alia University, where my supervisor, Professor Jantkumar Shah is there. And I also want to thank my group in ISA Kolkata. And there are some people from our group are missing, like Rohit Hazra or Dr. Shadukhan or Shimon Shadukhan, Anjun Shadukhan. They are not here because I don't have a group picture with them. Okay, so thank you for your kind attention.
I'm looking
Thank you very much.
Here. Thank you so much, Santanu, for this interesting talk. So let's start with the questions. Does anyone have a question for Santanu?
I do have some questions. I don't know if Santanu, thank you very much for your presentation, for your work, and it's really interesting. I have a couple of questions. I wrote some of them in the chat, and but the first one is like I was wondering what happened if you consider the limits regarding the potential in the first part of your presentation. You have this step model, and I was wondering what happened when V0 goes to 0. What happened with the Shannon entropy and the Fisher entropy if you take V0 goes to 0?
I think there will nothing happen. Like a wave packet was coming, the width of the potential is 0, so it will see no well, so it will just pass through. So I think the potential, the Shannon entropy will be constant, will not change. That I think.
Okay, wouldn't you consider that it's like it goes to infinity somehow, because it's like a free particle potential, right? So in that case, the Shannon entropy will be like infinite.
Yeah, that's true. Yes, that's true. If we consider a free particle, the wave function will be a plane wave. It will not be able. You will not be able to normalize it, and you cannot even define the Shannon entropy. It will go to infinity. Now the thing is, if you consider the wave packet, what I have shown, it will have finite width, but it will have a very high width so that it can represent the a wave packet which will correspond to a free particle. Then you can have you can normalize the Gaussian wave packet, and you can have a finite value of the Shannon entropy, and the Shannon entropy will remain constant if the potential is 0.
Okay. Interesting. And in the other case, in which the width of the potential goes to infinity, what will happen there?
Okay, so the thing is that there will be the wave packet will be completely trapped inside the potential, depending on the interference, what kind of width or depth we are considering, and depending on that, there may be full reflection or full transmissions, but it will depend upon that interference coming from the two wall of the well. Okay.
Yeah. My questions are driven because in the sense that is it possible to trap somehow the wave packet within the well, and if it's possible to have some sort of then you can consider entanglement with another well, and construct qubits or some sort of qubits, and so on. That's what motivates the questions. Okay. I don't know if I have more time for questions.
Nobody is raising his or her hand. If you have questions, colleagues, please raise your hand. And if you have another question, Alejandro.
Yeah, I do.
Yes, please.
The other question is related with the other model, because it's I really like it. Is the ion electron interaction. It's one of the fields I've been working with Humberto Laguna, but in a different approach using Bohmian mechanics. And I was wondering if it's possible to consider two things: the role of the initial conditions for the particle, for the projectile, and the time of arrival of the projectile. Whether it's possible to explore in the first case how the initial conditions shape the Shannon entropy and the Fisher information, and the time of arrival. If it's possible to explore the time of arrival distribution of the projectile. Those are my two questions. Yeah.
That is a really good suggestion. I have to see about that. Yeah, that is a really good suggestion. Thank you.
Okay, thank you.
I knew that you were going to ask this, Alejandro.
Yeah, totally.
So let's Yayanta to.
Yeah, thank you very much, Laguna, for the invitation and the notifications and arranging the seminar. Somehow the video is not working, so I'm sorry. But I have many questions, and I don't want to bother Santanu for a lot, because I think he is coming for India within few days. So I should have some more time to discuss with him with this nice and interesting talk. I should also congratulate his host and dear friend Professor Trujillo for the nice work. And I am sure that you are in very good hand for your postdoc career. Just to have one question which is coming to my mind, that whether the impact parameter theory is coming here, right? So whether we can have a solid quantum mechanical, full quantum mechanical theory like that of, say, for example, for the post-collision wave function, can you consider at least for the high energy regime, can you consider the Born approximated wave function for the higher orders? Can we do that, or is there any specific reason? And for the low energy collision is a kind of the partial wave analysis kind of thing to have a full quantum mechanical theory. This is the one, and the other one I think I get lost. No. The thing is whether you have tested for the first problem, whether you have tested that the BBM inequality is working when the oscillations is coming. I mean the Ramsauer-Townsend effect is happening. Okay. Or is it really have some significance or not?
Okay, so regarding the first questions of applying more quantum mechanical versions, In the present work, I have not done it, or we have not done it, but in several work, Remy has already applied iconal approximations or some kind of things to capture the full quantum mechanical version. But it is possible and it can be done. But at the present, I have not applied, and in future we may think about that. And for the BBM inequality, the second one, I have not tested, because for the BBM inequality, you have to find the total entropy coming from the position space and the momentum space.
Right.
In the first work, we have only concentrated on the position space. So we did not have the scope of getting the momentum space, but that can be done.
I mean, the reason I asked this question, the specific reason that I asked this question, that this complementary between the Fisher and the Shannon in the complementary spaces is because of the, I think one of the reason is the validity of the BBN inequality. So as you have said that the Fisher and Shannon entropy follows each other, the pattern follows each other. So whether is any kind of violation of this principle or not?
Yeah.
Maybe
because the way we approach with the problem, getting a momentum space wave function is computationally really expensive. That's why for the timing we kept it aside. We only concentrate on the position space. Yes.
Okay, okay, thank you.
Thank you.
Thank you, Professor Yojanta, and thank you, Shantanu. Before I give the words to Adrian, I'm looking that there is a question in the chat from Professor Juan Carlos. I don't know if Professor want to ask Shantanu.
Yes. Can you hear me? Can you hear
Hi,
me?
hi. Yes, I can hear you, Professor.
Okay, thank you. So it's because I found very interesting the results grounded on the separate states study of both Shannon entropy and Fisher information. And this is what I'm wondering about the eventual interest on analyzing the time evolution of the collision processes along the Fisher-Shannon information plane.
Yes.
Corresponding complexity measure, for instance.
Yes. We are also doing that. I have only shown the variation of the Shannon and Fisher, but we are also analyzing all the results, and one of the best way to see the Fisher-Shannon plane. We are also in the process, and thank you for the suggestion also.
Okay, thank you.
Thank you, Professor.
Thank you. So please, Adrian, Professor Adrian, go ahead.
Thank you. And thank you, Shantanu. Very nice talk. So just two questions. One is, since you are working with these measures, I was expecting that resonance of the wave functions will appear eventually in the entropies, right? But I don't know if there is a new emergent hidden or feature in the entropies that cannot be seen in the wave function. So this is one question.
Okay. Let me answer you. When we do that, see, everything is coming from the probability density, and we expect something what we can estimate will be reflected. If we estimate the entropy, it will be reflected the same information coming from the probability density. I am not demanding in that word that I am doing something very different from the probability density. Rather, I should safely say like that, we are giving another degree of the property that can also explain the similar thing, like the wave function based measure. Okay, and if you calculate the probability, for example, if you have the probability density, then it is difficult to understand from the probability density distributions that whether that electron probability distribution is very delocalized or localized. if you calculate the entropy, you can exactly say how dispersed the cloud is. So it is another degree of freedom which can give something maybe inherent in the wave functions, but we can give the thing in more explicit way. That is my explanation.
Okay, thank you. Yeah. And the second is just have you considered also time-dependent potential? So you already have time dependence in the problem, but I don't know, the deep
No.
can be changing, and
Yes,
if you have
yes,
some
yes,
results
yes.
or something about it.
Yeah, in our group, we are also trying to do that with some particle having some oscillatory potential or time-dependent potential. We are trying to do that, but for that problem, we have only considered that static one.
Okay, no. Thank you. Very nice talk. Yeah, thank you, Shantan.
Thank you, Adrian. Thank you.
Yeah.
And another question, colleagues, for Shantanu? Okay, if not, let me thank Shantanu for the talk, and let me say, Shantanu, that I think that many of us are expecting your momentum space work, so it will be nice to see.
Yes,
To see.
yes,
And
yes.
I think that your work is very nice, and is I mean it shows very intriguing aspects on the problem of collision. So thank you. So please, Rodolfo.
Thank you again for inviting me.
Nice, our pleasure. Rodolfo, are you going to close the seminar?
Well, I don't know if Robbie would like to close the seminar with some thoughts.
Okay. No, Shantanu, thank you very much for your talk. If I might, I just have one question. So sorry.
Sure.
Okay, please,
Yeah.
please.
Yeah, in Shantanu, yeah, thank you. In the last part, you spoke about the Stuckelberg oscillations, right? Yeah. Is there? I just wondered, because I have seen, and I can't remember now, but there is a quantity that's called the Stuckelberg entropy, right? So I don't know if you have seen that, but it might be, or what is the relation? I think, if I remember correctly, it's kind of like the discrete form of the entropy, that what you were talking about in the last part. So yeah, so it just struck me as
Okay. Thank you. I have not seen that, but I should search for it. I'll try to understand.
Yeah, maybe it might give something more to the problem. Yeah. Okay. So thank you. Yeah, very interesting. Very interesting with the collisions and the time and the dynamics. I think that's very interesting that there's movement towards dynamic systems now that was I think missing in the past, and I think you're doing a very important part there to look at the dynamics. Yeah.
Exactly, Professor.
So thank you very much, and yeah. So should we conclude for today, or I don't know if
just allow me to share some closing words, Robbie.
Yeah. Okay. So Rodolfo, please go ahead.
Okay, thanks. Okay, well, on behalf of the organizers of this webinar series, I would like to express our appreciation to all attendees for joining us in this second session of the International Webinar on Quantum Information Science. We all hope this initiative will become a regular forum, and I think it is going in good way to motivate scientific discussion and collaboration. Well, we are particularly grateful to Santanu for his interesting presentation. Thank you very much, Santanu.
Thank
we
you.
look forward to welcome you.
Yes.
Okay, thank you. We look forward to welcome you again to the next sessions of the series, which of course requires of your enthusiastic participation to keep the webinar series active and growing, so that we will be pleased to welcome your contributions, or any of your colleagues if you can share this information to them. Please feel free to contact any of the organizers, Humberto, Alejandro, Robin, or myself, to schedule a presentation, or perhaps to recommend colleagues from your institutions who might be interested in participating in this webinar series. So, saying that, we hope to see you on the second Thursday of July, at the same time. It's 8 a.m. Central Time, which is UTC -6. Well, we thank you all for attending this webinar series. For me, that's all, Humberto.
Nice. Have a good night in India and good afternoon in Europe and good morning in Mexico. So,
And viva
Adiós,
México.
see you.
Good. See you all.
Thanks to everybody for
Yes,
the attendance.
see you.
Good.